Welcome. And today we have another Tech Talk from VDE, specifically VDE Americas. And our topic today is how the Hail Resiliency Curve Test advances solar risk assessment. So this one is definitely near and dear to my heart. I've been helping with create this new Hail Resiliency Curve Test in collaboration with RETC and other organizations for a couple of years now. So I'm very happy to introduce this to as a topic to our webinar series, and also introduce some of the key people who worked on this. So with that, let's get going. Looks like there's some people in the lobby I'm going to let in here. All right. And feel free to send your questions in the chat. We will try to answer them during the presentation or get to them at the end. All right, so today we are honored to have two guest speakers, Sharif Kadir, who is the president and CEO of RETC, which is part of the VDE Group, same parent organization as VDE Americas, and also Mike Pilliod, who is the president and CTO of Central Tension, a glass consulting company. So let me introduce Mike first. So as I mentioned, Mike Pilliod is the president, actually the founding president and CTO of Central Tension. He has over 25 years in the glass engineering and structural reliability business. He formerly worked at Apple and Tesla, where he brought about a number of innovations, which many of us use. So thank you very much for that, Mike. Thanks for the fact that I can keep my iPhone for more than 10 minutes without breaking it. He is also a pioneer in the test of failure protocols using Weibull analysis, which is how he fits into the picture here, and an expert in solar PV glass, architectural glass, automotive glass, and also aerospace glass systems. I understand currently working with NASA and a spaceship company. All right, and then we have Sharif Kadir, who is the president and CEO of Renewable Energy Test Center, otherwise known as RETC, in Fremont. Sharif has been leading RETC since 2009. RETC specializes in equipment testing for the solar power industry, mostly PV modules, but also other equipment. He's also the co-developer of some of the solar industry's leading equipment tests, including the Thresher test, which is an extended durability test that I definitely have made use of many, many times. The Hail durability test, and now the Hail Resiliency Curve test, among other tests I think that we probably didn't list here. So RETC, as I mentioned, is a test lab based in Fremont, California, and they are the ones who are providing this this HRC Hail Resiliency Curve test through their the test simulation capabilities, which we will discuss later. And Sharif's vision is to one of his visions. I presume you have many visions, Sharif, but one of them is to move the solar industry from pass-fail to statistical reliability testing, which I think is a really good idea. All right, let's move forward. So today we're just going to touch briefly on VDE's Hail Risk Intelligence Services. We'll then move into a discussion with Sharif and Mike, starting with Mike, to understand solar panel glass strength and approaches to testing that glass. And then we'll get into the heart of the matter, which is the new Hail Resiliency Curve test from VDE and RETC. We'll then go into some questions, and at the very end, I'll talk about some new Hail Risk Intelligence Services from VDE Americas, and also some free resources. But before we begin, I want to acknowledge the many people who worked on the Hail Resiliency Curve test over the last couple of years. I won't name them all, but here they are listed in alphabetical order. And you can see we have 5 different organizations that all work together in the areas of test creation and actual testing, physical testing, weather, meteorology, statistical analysis, and then obviously glass engineering. So thank you to everyone who contributed to this important new test. All right, so with that, let me just briefly touch on VDE Americas Hail Risk Intelligence Services. So as you may know, we are the leading provider of hail assessment and mitigation services for the solar power industry. And as people may know, as most people probably know who are in attendance here, hail is a huge problem in the solar power industry. It doesn't account for a lot of claims, so only about 2% of the claims by count, but over 50% of the actual losses that the solar power industry is experiencing due to catastrophic perils. And in Texas alone, we had over $600 million in hail-related losses since 2018. So it's a big problem. But the good news is that we're solving it through our hail risk intelligence services. So just some of the things that we offer here, I'll just mention this briefly and then we'll get into the conversation. We offer engineered hail risk of loss reports. So these are probable maximum loss and average annual loss, and pro forma and downside loss reports that help you basically figure out how much hail insurance you need, how much coverage you need, and also help you model losses both on a pro forma perspective, like a P50 perspective, and a downside perspective. We offer a series of maps that give people the ability to very quickly understand the risk of hail using specific equipment, like specific types of PV modules, specific trackers at a particular location. We do reports that show the co-probability of wind and hail at the same time to understand how strong a tracker needs to be in hail stow. We also provide hail stow support for hail stow protocols. We provide a specification that includes a test specification and also ongoing verification of hail stow systems to ensure that they're working properly. We also provide product development support for hail durability for module companies, PV module companies, and also tracker companies. And then finally, we, in partnership with RETC, we're now providing the Hail Resiliency Curve testing that helps people understand what their a specific PV module with a specific bill of materials, how hail resilient that actually is. And that's what we're going to talk about today. All right, so I need to say that VDE is a company that was founded in 1893. It's headquartered in Germany. It was actually founded by Werner von Siemens, who is like the Thomas Edison or the Nikola Tesla of Europe. And the VDE Group, as we call them, owns VDE Americas, which is the company I work for, and also RETC. So we are sister organizations. All right. Well, with that, let's get into the conversation, starting with glass and talking about factors that affect PV module vulnerability and resilience in hailstorms. So with that, let me pose the question to you, Mike. What factors influence the intrinsic strength of solar glass?
Yeah, great. Thanks, John. Nice to meet everybody and present this to you. So Mike Pillard, I'm a glass engineering, glass science, and I've been working primarily on the product side. And hail was one of the areas that brought me into solar and to work on durable glass or understanding failure mechanisms. So there's a lot of aspects that affect glass strength, but primarily the two things to walk away with is glass breaks from pre-existing flaws and intention. So as we walk through the why glass breaks, just keep that in mind. There's pre-existing flaws and intention. But to start in glass composition and manufacturing process, this is to make the large sheets of glass. There's many different types of glass, primarily for the solar industry, and this also goes to architectural and automotive. Soda lime silicate is the primary glass used. For solar, it would be a high transmission or low, what we would call in the field, low iron glass. So if you looked at the edge of glass and you see a green tone to the edge of the glass, that's iron at very small parts per million in it. If you look at solar glass, you'll see a water clear edge, which means the high transmission. The iron doesn't absorb any light coming in, so it can maximize the efficiency of solar. Within the solar world, and this isn't 100% true, but the predominant in crystalline solar is patterned rolled glass, where they roll the soda lime glass through rollers to create either small bumps or some kind of texture onto the glass, and then go through a lamination process and cutting and grinding. Float glass is also used in solar as well, so it's not 100% rolled, but it is the primary one. With heat treatment or strengthening things, so that is, if you hear the words tempered or heat strengthened glass, what that means in the degree of soda lime glass is that you are inducing a secondary operation after the glass is cut and ground to shape. You go through a tempering process or heat strengthening process, which the goal of that in the bottom graphic is to induce compression stress on the surface of it, and it has an internal central tension limit to balance the stress balance within the glass. So all solar glass out there, and mainly if you looked at a tempered glass, if you break it and it breaks into small fragments, what's going on there is that there's a compression stress induced in the surface of the glass. And its primary job there, including in other strengthening mechanism, is to push flaws on the surface of glass together. So if you have a scratch on the glass, or if you have a scratch on your iPhone, there's a compressive stress that's pushing those flaws together and not allowing it to propagate through the glass. So this sort of induced compressive stress. The stress level, if you think about heat tempered and strengthening, I'll go into it in the next slide, but in general, it's the amount of compressive surface stress and then the depth of layer. So how deep the compressive stress goes into the glass. In thermal tempering, it's roughly about 20% on each side, and on the edges is compressive stress, and the inner 60% is under tension to balance that stress sandwich. Just for everybody out there, you can over strengthen glass. You don't want to have all the compressive stress. Eventually you need to balance it with a central tension inside to keep the glass nice and happy for it. Within the solar industry, there's 2 millimeter, 3.2, 4 millimeter. Obviously it's a continuum. If you can make those, you can make thicker or thinner ones that are out there. Within the architectural tends to be 5 millimeter and up. So solar is driving to thinner thicknesses relative to architectural that's out there. Hence, like kind of maybe the industrialization process of the things. Within the architectural, you tend to be a bit thicker than in solar. Like I mentioned before, surface quality and defects in the glass, these could be edge defects or these could be surface defects, matter because that's where glass breaks from pre-existing flaws. Just for everybody's information, if you go and you clean the window of your car or on in your house, you're going to induce small scratches on the surface just by cleaning. You don't need a deep gouge in the glass to cause a rate limiting flaw or a strength limiting flaw in the glass. These are in every surface of glass that's out there has pre-existing flaws that are on the surface. The goal of glass understanding is that it has a flaw distribution. Every piece of glass has some level of flaw distribution in it across the surface. And then at the systems level, when you go through how the glass is mounted, like I mentioned, glass breaks in tension. So how it's mounted, for instance, a cantilevered edge or where there's support structures. For instance, also if there's a hole in the glass on the backside for junction boxes, those edge conditions if you look at the graphic on the side, if you look at the side of it, those are ground surface edges. So you're cutting glass and you're grinding it. In a glass science perspective, you're inducing a bunch of flaws. Your goal of grinding is just to get it smooth enough and defect free enough that it has strength when you go to mount it in the solar module. We can go to the next slide, JP.
Okay.
So thermal tempering is the process for soda lime that induces the compressive stress. This is specific in this conversation into soda lime silicate. The material property that the glass needs to be thermally tempered is thermal expansion. What you do is you take the glass that's cut into the shape. So this is after grinding and after surface finishing. Typically, obviously before lamination, but sometimes before and after coating, but the glass is already to shape in the solar module. You heat the glass up in the heater to 20 degrees, up to about 600 degrees centigrade, and that's below the softening point of soda lime glass. So what it's doing is it's expanding the glass. It's still keeping its flatness, and then it goes into a fast, rapid cooling surface on the surface of the glass. And what happens is that the inner meat of the glass, the surfaces freeze, and the inner meat of the glass continues to shrink, thus pulling the surfaces into compression. So this is a fundamental thermal expansion property of the glass, and it gets heated up. The surfaces get frozen, for lack of a better word, with air pressure, and then the middle of the glass continues to shrink, pulling everything into compression. So the bottom right-hand corner, if you've worn polarized glasses or you see these small circles into automotive glass and architecture, if you see sort of ripples or stress patterns, especially with polarized sunglasses, what these are the nozzles that are cooling down the glass during this thermal tempering process. So another thing, if you walk away with those, is where you're getting differential stress patterns within the glass because where the nozzles are to cool down the glass. In flat glass, you would tend to have either ribbons or straight lines that would end up having sort of anisotropy where you'd think of, but you basically have like stress patterns that look like lines in your architectural solar glass. As you look at the stress versus depth thing, you have two curves here. One's a red curve of 2 millimeters, and one's a blue curve of 3.2 millimeters. And the way to think about it when I talked about compression and then attention is eventually within if you took a cross section of the glass, you'll go from compressive stress on the surface down about 20%, and it'll go through a zero stress in the glass, and then it'll go into tension. And then it'll go back to compression as you go through the cross section of the glass. When you go from 3.2 millimeters and you cool it down, you have more thermal mass inside of your glass, freeze the surfaces, it can pull it into compression. You do two things. One is you get a little bit deeper, a little bit more surface stress on it, as well as you get a bigger depth of layer because your glass is thicker than it. At 2 millimeters, one of the fundamental areas, it's not impossible to fully temper glass at 2 millimeters, but it gets much more difficult because you don't have enough thermal mass in your glass to cool down the surfaces and allow the inside meat of the glass to continue to shrink to get your surfaces into compression. One of the things that I do want to highlight here is within the glass tempering world, this is not a binary tempered glass or heat strengthened glass. Those are historical things from the architecture safety glass world. This is a continuum of how much surface stress you have in it and how deep the depth of layer is. For instance, when you look at what's considered heat strengthened glass in the industry, you have 3,500 to 7,500 psi. There's a significant difference between those, as well as it's a continuum. You can look at it as like how quickly you cool down your glass and what your thermal preheating is. You can affect that thermal tempering of the glass. And again, as you get more sort of like thicker glasses and you get to what they consider fully tempered glass, that's just a function of being over 10,000 psi. But I want you to keep in mind that these aren't binary applications. You want to look at two things when you look at surface compression into glass: how high the surface stress is on the surface and how deep the depth of layer is down through your glass. And again, the goal of most all glass strengthening is just to have compressive stress pushing together surface flaws. And we'll get into how glass breaks and things, but just keeping that in mind, most of the glass on your phone, the glass in your solar panel is bottled up. It's continuously pushing these flaws together on the surface to not allow them to propagate.
Hey, Mike, we have a couple questions.
Yes.
Alfonso Tovar notes that both illustrations of the horizontal cross-section tempered versus heat strengthened look the same in the slide. So perhaps you can talk about the difference. And then the next question is from Gautam Ghose. So is 2 millimeter the thinnest top glass can go?
Great. Yeah, great question. So on the right-hand side, the graphic there is just to illustrate that there's an inner tension area and an outer compression on the surface. They would be different based on the thickness of the glass. So as the thickness of the glass changes, you get a deeper depth of layer and potentially more compressive stress on it. But it's fundamentally a function of the glass thickness, the thermal expansion properties, and how the heating and cooling tempering. So those graphics are just to show that you have an inner central tension and a compressive layer. The reason I mentioned that is that you need a stress balance within the glass. If you continue to put too much compressive stress on your surface, you can get into the frangibility limit. So if you hit the corner of the glass, the whole thing shatters like crazy versus having a single line crack or a low stress crack. You can over strengthen glass in a sense. Doing a thermal tempering is kind of tough because you end up breaking it in the tempering process if you do that. But that's kind of the area. The reason I put these two up there is when you ask the questions about tempered glass, or you hear heat strengthened or fully tempered, you really want to jump into the details of what is the compressive stress and how deep the depth of layer. How deep does the stress go down to that 0 point in the glass? That would be considered depth of layer. Within the question
they look different when they break, also, right?
They look different when they break. Yeah. They look different when they break. And this is sort of a property called fragmentation. But usually, and it's not sort of not binary. The more stress you have in there, when you break it, a fully tempered piece, typically thicker, will end up in these sort of fragments that are there, which are non-sharp shrouds, so they are like shards in the industry. But that typically is for thicker glasses in general to get that breakage pattern. To the question of 2 millimeter glass is the thinnest front surface. That's a question of how much stress do you need to put into your glass. There eventually will be a fundamental limit based on thermal tempering in using soda lime glass. So as you heat it up and cool it down, right near 2 millimeters, it gets very difficult to induce the right level of fast cooling so the middle of the glass can continue to shrink. And it's why chemical tempering and other things are used in the cell phone industry and consumer electronics, because as you get sub 1 millimeter, it almost becomes physically impossible to cool the glass fast enough without thermally shocking it. In that thing. So I think for our things, as we go through it, going to 2 millimeters, you end up getting into you're just not able to induce enough compressive stress in the surface, as well as that depth of layer is a function of your thickness. So the 20% of 2 millimeters is less deep into the glass than 20% of 3.2 millimeters into the glass. So we can get to that with pre-existing flaws, but I think in general, as we looked at the solar industry, the drive to go to 2 millimeters seemed to be primarily dominated by weight of the modules, and Sharif can talk to the details of the history there. But that move to look at weight, but it also has a pretty significant area around the reliability of glass, especially in a 2 millimeter module. So I can let Sharif talk about the history of solar since he's been in it so long.
Yeah, perfect segue. Yeah. How have technology trends impacted solar glass strength, as noted in this slide?
Thank you, and hi everybody, and thanks everyone for joining. Historically, the modules used to be, everybody thinks of modules as having been very resilient in the past, and it's absolutely true. I mean, back in the days, glass on modules was usually 4 millimeters, and it got thinned down to 3.2 millimeters, and the industry freaked out about that trend. The frames used to be 50 millimeters thick. They were really, really heavy duty modules. These issues didn't happen. They weren't reported. But then installations back in the days when an installation got as high as 50 megawatts, people, threw huge parties. And so now with gigawatts and gigawatts being installed in high risk areas and the module size is increasing, things, you just increase the risk of breakage happening in the field. Now, as far as the module trends, everybody agrees that higher power modules are better for many, many reasons. You install one module producing 600 watts, for instance, is a lot better than installing 3 modules producing 200 watts each because of labor, because of the connections. You have 1/3 fewer connectors, which means 1/3 less chance of failing, right? The problem with the larger modules producing higher power, the ideal trend would be to just increase efficiency, but then reaching the physical limits of PV cells, the next thing to do is to increase the size of modules. Glass tends to account for the bulk of the weight of PV modules. Everything else is much lighter, and so if manufacturers want to reduce the weight of modules, the first thing they look at is glass. So there was an interesting trend back in 2017, 2018 when bifacial technology started to hit the market. There was a need to have light enter the module from the backside. And there are two ways of doing it. You can either add a clear backsheet or you can add a clear piece of glass. So taking a module that was getting larger and larger with a 3.2 millimeter front glass, adding another piece of glass to the back was just too heavy to deal with. And so manufacturers responded to a lot of criticism from EPCs and developers, and they introduced modules with thinner glass. I don't see personally modules with thin glass as being a problem. They're just a trend that needs to be dealt with. And the HRC aims to quantify the risk associated with those trends and identify ways to deal with them, like having mitigation strategies, either by increasing the thickness of glass or by adding other mitigation strategies. But this webinar is focused on what happened to the glass. But that's kind of the trend of the modules and what led to the thinning of the glass.
Great, thank you, Sharif. All right, so we're going to get back to talking about testing glass. Mike, could you talk about typical glass tests and what's pushing the solar power industry to create the tests like the HRC?
Yeah, you bet. Absolutely. It's a pleasure. So I've broken thousands, if not hundreds of thousands pieces of glass in my career of doing product development for glass. And the primary sort of failure modes in the sense of glass breaks in tension from pre-existing flaws, these three tests are sort of traditional styles of how you would test glass for fundamental glass strength. Ring-on-ring test is a shear test on either side of the glass. It puts together sort of a surface thing, and its goal of that test is to eliminate edge effects from the things. On the full right-hand side, you have a 3-point bend test or a 4-point bend test in other formats. And what that fundamentally is doing as you push it down, those grinding edges that I talked about on the edge of the glass, those are flaws that are in the surface, that are on the edge of the glass, which act as origins for glass breakage. So when you do a bending mode in that stuff, you're primarily looking at edge condition for 3 to 4 point bend testing. Ring on ring testing, you're doing surface stress. And when you do a ball drop in the middle, what that's looking at is doing a direct impact, a blunt force direct impact. You can also do an impact with a sharp impact, like a diamond indenter, where you're looking at sharp impact on the surface. As you drop a ball onto the glass or shoot a hailstorm at the hail ball at the glass, what happens with glass and it breaks in tension is as it hits the surface of the glass, the tension region's on the backside. So in that sort of bending moment, you likely are failing on the backside of the top glass or the backside of the bottom glass in that format as far as a blunt impact. If you took a sharp impact and put it onto the surface of the glass, you would fail on surface 1 or the top surface. All these being said, glass testing in general, or the probability of failure of a glass does not have a standard. If you look at a data sheet and you can look at the strength of glass has a probability of failure. So you need to test enough populations because the flaw distribution in the glass is different from one piece of glass to the other. So when it breaks and how it breaks might be different than the same population, the same exact sort of type of glass, the same processing, but those rate limiting flaws are different within it. So you need to do a certain population. And when you look at like kind of these like kind of the standards tests that are out there from a pass fail perspective in automotive, we did things like crash testing, where you're doing sort of a qualifying test for a module. These binary pass fail are not a bad thing as far as qualification, but what they don't tell you is if you pass it, how good did you get? How far away from failure were you? And if you failed, how close were you to the failure point when you failed? To do that, you need to do sort of what's called the staircase method, or be able to start increasing energy to be able to look at failures as far as when something failed. So the idea of the Hail Resiliency Curve is not to eliminate standards out there, but it's to develop a qualified level to figure out how well it is and do the development aspect to really understand the resiliency of a module versus does it pass fail criteria that's out there.
Yes, and you're the one who, you were one of the people who recommended this idea of pass fail, or sorry, test to failure, and application of the Weibull probability distributions. And I understand that you use that for the automotive industry. We have a slide on that coming up here.
Yeah, definitely. Yeah, if you look at if you look at for the automotive industry, the idea here when I was at Tesla was to address rock chips. Most everybody on the phone call probably has driven in a car and heard a rock hit the windshield and go through a very emotional response to the hit of a rock onto the windshield. And the way we looked at those probabilities to failure, so a Weibull curve in general, for those who aren't familiar, is on the y-axis you have probability of failure. At the top it's 99%, at the bottom it's 0.1%. So basically the way to read this, if you're whatever energy on the x-axis, in this case it was speed that the car was going, which I'll explain a little bit later, but sort of some level of energy or on the x-axis and a probability to fail on the y-axis. Within the automotive industry, what I had to do is went around and collected a bunch of rocks that were on the side of the road to figure out what gets kicked up by the car behind you and what type of rock hits the windshield. In this sense, roughly about 2 grams of a rock, of a sharp object that would hit it. And what we did is took a look at in the right-hand side is looked at different types of glass, different constructions of glass in the different colors. So all of the colored dots are the same, quote unquote, the same type of glass, the same processing. And what you're looking at there is different energies to failure and actual data points in it. And then you're plotting those into Weibull analysis on a log-log curve to get the parallel lines. The interesting part of this and why it's relevant for our discussion here is all of these are glass breakage. All of these dots are failed glass in the thing. So you have to fail the glass to get a dot on it. And you keep on increasing the energy or the height of a drop to be able to get those dots that are there. And when you plot these on what you're looking for is a statistical difference between two populations. So the maroon line and the teal line that are fairly close to each other there still is somewhat of a statistical difference. But if you don't overlap at all, for instance, the dark blue line, you can be assured that your maroon line and your dark blue line are different populations and also different statistical differences between those populations, with the dark blue being much better than the maroon line. With the middle section there that's highlighted in light blue, the rectangle, what those were an idea of typical vehicle speeds that are out there. So I think one of the things as you look at test to failure is, and understanding the glass breakage, is if you get, say, 20% better, for instance, that teal line and the maroon line, in 40 miles per hour to 90 miles per hour, you might have gotten 20% different, but you're still in a very difficult area around probability of failure under typical vehicle speeds. To sort of address rock chips, you want to be outside of that light blue rectangle into that far to the right area where you can have confidence that if you're going 80 miles per hour, the chance of that windshield breaking if it gets hit with a rock is down into the sub 1% failure rate of that one, to be outside of the red zone, if you will. So I think that's something as we look at the Hail Resiliency Curve is to really be mindful of is if you know modules are breaking under hailstorms, it's how much better do you need to get at a typical vehicle speeds or miles per hour of hail or kinetic energy of hail thing. So you got to test enough glass to get a good statistical population, and you have to continue to test it because the way you make the glass, the way you temper it, the cut and grinding, the processing of the solar panel has a huge effect on your outcome. Or if you change glass vendors or you change manufacturing locations, you want to make sure you test a good population of glass to ensure that your hail resiliency or your, in this case, rock chip resistance are confirmed.
Great, excellent. Thank you, Mike. All right, let's move into the next part of the conversation, which is actually about the Hail Resiliency Curve Test. And with that, I'm going to pose this question to Sharif. So Sharif, in 2019, RETC introduced the Hail Durability Test. How did the HDT improve on IEC testing, but also what limitations did it have, or does it have?
Yeah, so in 2019 happens to coincide with a famous hail event in Texas. But the work actually started before that. So as I mentioned earlier, in 2017, 2018, there was quite a bit of interest in bifacial modules. And we started seeing modules of all kinds of different constructions, some of which, or many of which, were dual glass construction with 2.5 millimeters, actually ranging anywhere from 2 millimeters to 2.8 millimeters, as manufacturers were trying different thicknesses. And one of the things that we noticed at the time was that as we were going through our standard suite of tests, we started seeing a signal that we hadn't seen before, which is modules breaking during hail testing, standard hail testing. And historically, we did a lot of hail testing for modules installed in high-risk areas. And the standard method was to perform hail testing using 2-inch millimeters of test. So one thing that we did in 2019 was collaborate with Kent Whitfield from Nextracker and in trying to figure out how to mitigate this, knowing that there was a risk out there with modules being shipped with thin glass that would be susceptible to hail damage. And the limitation that we had, which is in retrospect was, it kind of makes sense now, but one of the things that we did was we had assumed that we could come up with a program that was binary in nature, which is determine whether modules were good or bad, whether they could survive a hail impact or not. And that is noted here, I think, in the graph. And so what this graph illustrates is hundreds, if not thousands, of modules that we had tested of different constructions. The graph actually comes from a much wider graph that we generated with many different thicknesses, different constructions, different sizes of modules. And this one just compares the 2 millimeter construction to the 3.2 millimeter glass construction. And you can see a clear shift in risk of damage between the 3.2 millimeter glass and 2 millimeter glass. But one thing you can easily note here is the uncertainty band around every point that we took. So we had a limited number of impact or kinetic energies that we subjected the glass to, the modules to. And we just grouped them by kinetic energy. That's all we did. So we took all the 2 millimeter glass modules, all the 3.2 millimeter glass modules, and we compared them for every kinetic energy. And the kinetic energy here is noted by the as a function of the ice ball diameter and velocity. So sometimes there's an uncertainty around that as well, based on the weight of the ice ball and the velocity. But the driving factor here on the uncertainty is really the different constructions and the fact that we were only looking at pass-fail criteria for specific kinetic energy. The revelation there is working with our sister company, as John Peritelli noted, the VDEA team was and many of our partners was realizing that this is a probabilistic function, not a binary function. And so what that required is it requires us to understand the probability of failure, not whether a product fails or passes. And the probability of failure can be reduced or increased depending on the module construction as well as the mitigation strategy. So for instance, if a product, if a module is sitting flat in an area versus tilted, it changes slightly the probability of failure. And at the same time, the construction of the module plays a big role in that probability of failure, regardless of how the module is installed. So yeah, so the HRC really is the next step up from the Hail durability testing, which is essentially how do you go from trying to determine whether a product fails or passes to understanding the statistical nature of that issue. And I think, JP, you can explain this a little bit better.
Yeah, okay. Well, I don't know if I can explain it better. I can explain it. So, yeah, so we developed this this Hail Resiliency Curve Test. It is, as we were talking about, it's a test to failure where we require at least 25 PV modules, ideally randomly selected from a batch of modules representing a particular bill of materials or a set of components at a that's manufactured at a particular location, or at least, you know, having enough material significance or difference from other bills of materials to be a distinct bill of materials. So we take 25, at least 25 of those modules, up to 30. So basically a pallet of modules. And then what we'll do is we will shoot freezer ice balls at them at random locations using higher and higher, larger and larger diameters and higher velocities to increase the kinetic energy until we have glass rupture of the modules, or perhaps the modules will not break if they're super strong. And so we will do that in the center region, the edge region, which has, you know, different glass breakage, different strengths essentially, and then we'll weight the results of those tests based on the areas of both of those regions to come up with a Hail resiliency curve that we use for modeling. And then and the way we came up with that curve is we take that data, basically the failure data and compared to the impact energy, and we will plot it on using a Weibull approach developed by a engineer and scientist named Weibull in the mid 20th century. And what we come up with are these Hail resiliency curves, as are shown here in this chart. So, you know, they're in the same shape as the curves that Sharif was talking about before, but they don't have the same level of uncertainty. So we don't have these large uncertainty bars anymore. So these are much more accurate depictions of the probability of failure based on impact energy, or freezer ice ball size, or naturally occurring hail size. You know, we can essentially translate the impact energy into those other units for modeling purposes. And that's what you would get if you get a Hail resiliency curve test in the test report. You get these Hail resiliency curves for your module in all those different sort of comparisons: probability of failure to impact energy, naturally occurring hail, freezer ice ball size. And so you can really get a sense of how your module performs in real world hail conditions. And I'll talk about that a little bit more in a moment. But let me hand it back to you, Sharif, to talk about the actual testing in a little bit more detail.
So yeah, and I think one thing that's really important to note here, if you can go to the previous slide, JP, that I'd like to explain further is when we perform IEC type testing or UL or ASTM or FM type testing, where there's a table and you take a module and you perform, you randomly select certain locations and then you impact it. You have a limited number of opportunities to break that module, and when it breaks, you don't really have a statistical representation of what could happen in the field. Now, one of the things here that's important is the bullets there that say that we pick a central region, we impact the central region, the edge, and then do an area weighted distribution, right? So the way to think about it is in a typical hailstorm, if you take a 1 meter squared area or 2 meter squared area, which is typically the size of a module, give or take, if you study a hail storm, you're going to see there's going to be a probability of distribution. There's going to be small hail sizes and large hail sizes, and then those are going to come in various densities. So there are going to be a bunch of them or fewer of them, and they're going to fall in different regions of the module. Some are going to fall in the corner and the edges, and a lot of them are going to fall in the center. And the reason why these curves are so tight and so accurate is because we take all of that into consideration. So, it goes into the plan. And that's why the key here is we just keep impacting until the module breaks. And we impact certain areas until the module breaks. So we take into account the statistical nature of how a hailstorm could damage a module. And then go into the next slide is how we do that. We do that very simply. There's really no magic to it. We spent an inordinate amount of time figuring out how to make ice. It turns out to be very simple, but quite complicated to get there. So we make very clear ice. We reduce the inclusions to an absolute bare minimum. And the reason we do that is for a very simple reason, is for one simple goal, and it is to make the impact as repeatable as possible. So that if we're trying to impact, say, 20 modules with a 2-inch ice ball, we want those repeated impact to be as close to each other as possible, so that the kinetic energy that actually the module sees doesn't vary from impact to impact unless we want it to. And we do that by, as JP noted, by increasing the ice ball size or the velocity. So we impact the modules using a pneumatic cannon. We make ice. We mold it into very accurate spheres. We measure it right before impact, so we know exactly the mass. We measure the diameter, and then we measure the velocity with lasers, so we know exactly the kinetic energy upon impact. That's actually measured, and it's really good. It's very repeatable. So that's how we are able to contain a lot of these variables in our testing.
Great, excellent, thank you. So can you go into a little bit more detail in comparing it to the IEC 61215 standard?
Yeah, so with all standards, usually they provide a list of tests that are required, and then they provide some leeway in how the tests are performed. And in the case of hail testing, there's a very clear table in the standard from as long as the standard has been around, at least in recent times, that has allowances for performing hail testing anywhere from 25 millimeters, which is 1 inch, all the way to, I think, 75 millimeters. But the standard never required anybody to pass hail greater than 25 millimeters. So every manufacturer did what every manufacturer would do, pick the lowest, easiest test, pass it, and move on. So what we do instead, and what we have been doing since the HDT days, and even pre-HDT days, and then now into the HRC time, is we test well within the standard guidelines and beyond the standard guidelines. Our goal is really to try to represent what happens in the field. We perform the test in systematically selected random locations. And what I mean by that is we do random locations, but within certain areas. So for instance, if you just do a random set of locations, you may not have enough locations cover the edge. And so we segment the module, and then within the segments, we have a random location generator that allows us to account for the randomness nature of hail. And then we were like, as JP mentioned, we just perform the test and we just keep increasing the kinetic energy until the module breaks. And that tells us the resiliency of that module. And then all of that data is collected and it's fed into the brilliant minds of our engineers at the VDEA team, and then an HRC is actually developed. The actual HRC curve is developed.
Great. Excellent. And here's an example. Yeah, go ahead.
Yeah, I was going to say one thing to get comfortable with for the whole team here is that it's okay in glass testing world under controlled environments, just keep hitting it over and over and over again until the glass breaks. You're not especially with a blunt impact on surface one, you're not likely introducing flaws when it sees an ice fall and it doesn't break. And you can then increase the energy, hit it in the same location, if you will, and you're not likely inducing flaws that would end up being rate limiting into that thing. And that's sort of something to get comfortable. It's okay in glass world to do a staircase method, which means it didn't break at this height. You increase the height, same piece of glass, just keep going until it breaks. That's a very, very common thing in glass probability, durability to understand here in the hail resiliency. So there might be some areas like, oh, it just tested that piece of glass and it got weaker. That does not necessarily happen within a controlled environment within a lab. You can do this sort of staircase method, very common in glass testing to do that.
Yeah, Mike, that's actually really, really interesting. And that's really important to note. So when we developed the HDT initially, one thing we noticed is the way we performed the testing is we always started in the central region, and then we moved to the perimeter and then the corner. And then we always, our engineers always, came back and they'd say, hey, listen, I think they thought we were weakening the glass by impacting it in the central region. And by the time we get to the perimeter and the corner, it was already too weak. And so one thing we started doing is we started reversing the order, and we found that you impacted glass in the corner and it was just more likely to break. And so that's right. Absolutely a very important finding. And it took us, we had to learn it from scratch, but that's really, really important aspect of the testing.
Yeah, that's really interesting. Yeah, that makes sense. Okay, and here's an example of our first customer who used the HRC. The company is Earthos, and they co-developed a 4mm front glass, 2mm back glass module in collaboration with the module manufacturer Imperial Star. And yeah, they have a very strong module here. One thing to note about this module is that it has a special setup that represents Earthos's mounting scenario, which is directly on the ground, so it's not on a tracker. And so some of this hail resiliency could be due to not only the thicker glass that's fully heat tempered, but also the fact that this module is resting on the ground, which may dampen vibration and reduce flexing. But yeah, what we've done here is we've compared the Earthos hail resiliency curve, which is here, and I think this is like a navy blue, to those curves that Sharif was showing before for a typical 2mm dual glass and a 3.2mm polymer glass construction, and including the error bars. And yeah, you can see that their module is much stronger. One thing I'll notice that it actually is, it's should be stronger in this higher kinetic energy of impact area. And this is probably an anomaly that is associated with just the difference in the way the data was plotted. We used Weibull for, as we've been talking about, for the HRC from Earthos, and these other curves where we used a different type of statistical analysis. So this is essentially an example of our first customer. Sharif or Mike, do you have any comments about this?
I just think from a population perspective, if you take the gray line and you look at the kinetic energy and then the probability of failure, when you compare those to even the yellow or the blue line, at say like 100 joules at that section, that's where you're seeing that sort of super, like a very high statistical difference in the population, especially for the Earthos module. You're below 0.1% or 10% of the population that's going to break under those energies predicted. In the 2.2 glass, you're upwards of 100% of the modules. So it's not a surprise if you had a hailstorm come through that exists anything around 100 joules, you're going to be seeing a lot of breakages in your 2.2, and a decent amount, up to half, in your 3.2 type of thing. So that's the way to read that. Is basically population of the amount of population of failures that you would see within a solar farm under certain energies. So your goal is to be, far to the right, and then try to be as vertical as possible from an ability to predict stuff.
Yeah, that makes sense. Great. So I won't go into a lot of detail here, but as Sharif talked about before, and I touched on as well, this is used for modeling the actual risk of hail loss at different project locations. So these are some examples of different probable maximum loss figures at different severity levels, essentially downside levels and whatnot. And actually, these are average annual loss estimates. So yeah, with that, let's go to questions. I know we just have a couple minutes, so let me look at the QA. So see, we have a question here from Stavros Mastarokas. What are the angles evaluated on the tracker system with the different thicknesses of glass? Earthos is 0 degrees. Yeah, we use 0. We can tilt if needed, but yeah, the test uses 0. Next question is, how do you replicate the hail impact distribution on a solar panel from a real hailstorm? Well, that's what we were talking about before. So yeah, we have those two regions, the central region and the edge region, and we basically hit the modules until they break. Sharif and Mike, feel free to chime in here. I'm just trying to get these out of the way as quickly as possible. Next question is the proposal for manufacturers to obtain one curve representative for a given product as a hail resiliency certification? Sharif, you want to take that one?
I'm sorry, what's the question again?
Is the proposal for manufacturers to obtain one curve representative for a given product as a hail resiliency certification?
Yeah, to be honest, I think at a basic level, manufacturers should perform the test normal, with basically direct impact. That provides the worst case scenario for an installation for a PV module. And that I think it provides guidance in terms of the risk. However, if mitigation strategies are employed, like stowing, et cetera, then those should be considered, because they would shift the hail resiliency curve, one way or the other. So this is, in my opinion, it is recommended, and the reason is because more and more installations are going into the hail belt, where land is cheap, and more developers, as well as financial institutions and insurance companies, are becoming more nervous about those installations. And so having this information could greatly relieve that stress on the financial community, and could help with the project financing and insurance.
Yeah, I also think in general as well, the reason to do a good population of something that's considered the same bomb, the same processing, the same detail is if you do just one test of our binary and pick one module and test it or a couple modules, you could get lucky and get one on the high side, or you could get unlucky and get one on the low side. Is you want to get a population to be able to see what is the statistical probability. Even in the Earthos module, if you, for instance, if you tested one and it broke at 100 joules down at that 0.1%, it's possible that out of 50 modules, you pick one and that one had a rate limiting flaw that was on the low end. It's very important to do upwards of 20 to 25 to be able to get a very statistical distribution or flaw size distribution in your glass to give you predicted probability of failure under certain energies.
Excellent. We are out of time. I will keep it going for a couple more questions for people who can stay a little bit longer. But yeah, I wanted to thank everyone for attending if you have to go, but we are going to keep going with a few more questions for people who can stay longer.
And I tried to address some of the questions online. I replied to some of them when I realized we were running out of time. But yeah, you're right. We can stay maybe a few more minutes and answer a few more questions if people want to stick around.
Okay, great. Okay, one question is from Gautam Ghose. Do you bomb Hail one at a time or together, like real world? So answer is one at a time. Yeah,
and I answered that, and there was a follow-up which I can also address. So the test is performed sequentially, right? And one of the most common question is, well, in the field, you're more likely to get multiple impacts at the same time, right? Because you have a bunch of hail falling all at once. I think the critical point there is the point that Mike made earlier, is impacting a module once or twice or 100 times is not going to weaken it, because and this is the follow-up question, that's because the failure is determined by the inherent flaws of the glass, right? Which and the compressive strength of the glass, which is the tempering. And so impacting it once or twice, or two, hitting it with two shots at the same time, I don't think it will make a difference, because if anything, it will confuse the data, because if we shoot it with 5 ice balls at the same time and it breaks, you're going to have to figure out which one broke it. So once at a time, I think is fine. It takes longer, but I guess no, you can't figure out which one broke it, because you figure out where it actually broke.
One of the things that the pictures of, when a hailstorm goes through a solar farm, it gets a checkerboard pattern. You get one module next to another, and this one's pristine, and this one has 50 different breaks on it. And it's not that one had the one that broke got 50 rate limiting flaws on it. Glass breaks from pre-existing flaws. So if you get one hail ball that hits it and breaks the glass, any subsequent next hails is going to cause a failure, because you guys have a crack already in your glass on the front side. So typically what you would want to look for there on a glass perspective in a one-time event in a lab or in a hailstorm is one's going to cause a strength limiting flaw or a breakage, and then it's over for that piece of glass. It will get hit a bunch of times and create more hail failures. But those could have not have been rate limiting or strength limiting flaws inside of it. So having this go into the increasing the energy. Now in the field, there's other driver factors over time that could weaken the glass, environmental, corrosion things. This is in this test for our perspective is in sort of a one-time event to take it in a lab and controlled environment and continue increasing it in order to break the glass.
Great. There's a question here from Kevin Mayer. There have been some recent results from groundwork on glass breakage not being a pure function of impact energy, for instance, elastic collision assumption. And that when impacted at an angle, collisions include meaningful inelastic components, reducing the predictive benefits of hail stow. Are you seeing similar results? If so, how are you handling the transfer of your energy-based Weibull curves to impact at an angle? So yeah, I'll take that one. So yeah, that is a very good question. So kinetic energy versus momentum, or perhaps some other approach that needs to be used to model the probability of glass breakage at different angles, like an energy balance equation. So yeah, we are we're looking into the possibility that momentum is a better approach to use to simulate the effect of tracking. And this Hail Resiliency Curve can be used though for both approaches, the kinetic energy approach or the momentum approach or something else. It actually doesn't, the base Hail Resiliency Curve is applicable to any sort of modeling approach.
Yeah, and I think it's an awesome time to test things like that out at a systems level, and also a thing just because in order to gather the data, you need to break the modules. It's required. It's not even a question around things like you need to break it and figure out at what energies under a normal population. So you need to test enough as well as need to control enough and figure out, where are the tension regions, where are you hitting it? For instance, like Sharif mentioned, the edge conditions versus the center mass. As we mature, like the test more modules as well as more locations, you're going to gather up more. All those dots on the curve are broken modules, and not an assessment of would it break or did not break. You want to create that data and then plot the data to the best, probably like kind of your best your best confidence to figure out kind of at what energies would it break. So like being able to have a system that you can break a lot of glasses is a great starting point to start to collect that data and validate off those sort of details.
Yeah. Here's another question from Kevin. Noting that the Earthos testing included the effects of specific mounting with more support on all sides to reduce deflection, do you ever test modules on tracker mounting? For example, an impact on the short edge of a module on tracker mounts with large enough hail might cause meaningful deflection. Yeah, that was the first actual test. When we were testing the test, we tested a 2 millimeter glass module on a typical tracker mounting structure. So yeah, that could make a difference. We did not test the modules that Earthos gave us on a tracker to see how much of a difference that would make, but I suspect it does make a big difference. Sharif, do you have any comments on that?
No, I think that's just, the way it's, we are looking into that anyways. We try to cover as many scenarios as possible, but yeah, you're correct, John.
Yeah. Next question is from Gautam Ghose. How do you model the fact that in the field, the modules will get hit by hail many times that will probably weaken the modules for future failure? How do you replicate those conditions in the lab? Mike, do you want to address that?
Yeah, I think it's unless those previous ones that got hit a bunch induced flaws into the glass, it's unlikely that getting hit with a bunch of different hail balls significantly weakens the glass. And the reason for that is that and maybe JP, if you can go to the like the curve of just showing like when a blunt impact or a hail ball hits the glass, what goes on, or maybe just the graphic at the appendix, JP, with the curve and the ball on it showing the tension regions. Yeah, in this one here, typically in glass fracture mechanics, glass breaks in tension. So if you hit a hail ball, under the hail balls in compression, the backside surfaces are in tension. The question is, do those hail impacts cause surface damage, significant scratches or surface damage on the glass, and end up weakening the glass? And to be honest, I think it's an unknown area of like, as a hailstorm comes through and there's good modules that did not get broken. From a glass perspective, you would start with the hypothesis that the glass did not get weakened in that scenario and then prove it out things. But I wouldn't assume because a hail balls hit the glass that it significantly weakened the glass or changed the probability to failure. Same way as the staircase method, if you just keep hitting it, there is a valid assumption of test methods for glass that you did not significantly weaken the glass with a direct impact on the side. Now, for instance, if the hail hit the ground and a rock came up and chipped the backside of the glass, that's a scenario where you would weaken the glass in that situation.
Great.
Sounds a little weird, but you can keep hitting glass over and over until you find the rate limiting flaw that at what strength, and then it breaks. So yeah, it's a bit of a different approach when it comes to breaking glass.
We have a question. I'll just do a couple more questions. We have a question here from George Schmauder. What about cell breakage? Even if the solar glass did not break after an impact, the cells can be severely damaged. Does the HRC only consider glass defects? Yeah, that we're only considering glass breakage or glass rupture, so not cell defects. Sharif, do you want to talk about the reason we're doing that, or should I?
You can. I answered it, but you can. Yeah. You can
Oh,
give
you answered it already.
Yeah.
For some reason, I'm not seeing your responses, but yeah,
Oh,
I mean,
I'm sorry. Yeah, I just did.
no worries.
Maybe only the sender sees them. I apologize. Yeah, but
Yeah, no worries, no worries. So yeah, but cell cracks, we don't think they're as big a problem as they have been in the past because of all um, the bus bar connections.
Well, let me give the answer I gave there. So
Okay, great.
So we have two programs. The Hail durability test is not dead in the water. We still use it. A lot of manufacturers still use it. A lot of developers still require it. The difference is there are two types of risks out there. You have catastrophic risks when you have a devastating hailstorm that completely decimates a power plant and you have 70 or $80 million losses, right? And for that, what we're looking at here is the HRC to help determine how likely and how much money do you stand to lose if, given your construction, your installation method, and where you're going to be, right? The HDT is designed for the next question, which is this question, and it is, okay, modules survive, now what? Well, if they survive, sometimes you can have cracks. There are a lot of the cracks, as JP just mentioned, because there are so many bus bars, simple cracks do not matter as much as they used to when we had only 2 or 3 bus bars, because you could have a big chunk of a cell that gets isolated. Now we have 10 bus bars, whatever more, 16, 18 bus bars. So if you have a crack, more likely the photons are going to hit, the cell, and electrons are going to get collected no matter what. However, there are certain types of cracks, like spider web cracks, as they're noted, that will essentially cause some shunting in the cells. And those are going to be hotspot risks, which we still see. And that's the HDT product that we also, or service that we also offer.
Okay, great. This is the last question from Todd Karen. Let's see here. He asks, sorry, where is it? He asked about, I can't find it now, but he asked about the number of modules needed for this test. This test is pretty expensive. It does cost $45,000. That's how much we're asking for per mod. But yeah, can just 10 modules be used, as Todd was suggesting, after the initial test is done for different bonds?
Yeah, and I answered this. I mean, the very first snarky response to Todd, and Todd is a good guy, I know him very well, is that, well, I mean, the cost of this test is a lot cheaper than the losses, developers tend to incur, right? I mean, $70 million loss is no comparison to the cost of this test if you can avoid such damage. But of course, we can reduce the sample size, but it just comes at the expense of uncertainty and accuracy, right? That's basically what it comes down to. And so this sample size is what we feel comfortable with in order for us to generate a reasonably accurate hail resiliency curve, characterization curve that the industry, the developers, the financial institutions, and insurance companies can actually feel comfortable trusting, and it provides a reasonable accuracy. There is a question I'd like, maybe this is for you, JP, is it's from Smith, a gentleman or a person called Smith. It says the real information usable to developers where glass actually starts failing, what size of hail and what speed and direction. And so the question is this information covered in the HRC report? Do we provide, okay, well, this glass is going to fail if it sees this type of storm?
Yeah, we do. So what we do is we show several charts like I'm showing here, but some of the charts, instead of showing kinetic energy, show naturally occurring hail size in the x-axis here, based on a study by a scientist named Andy Hamesfield. So you can basically convert the hail resiliency curve to plot the failure probability with naturally occurring hail sizes of different diameters. And then you can take the meteorological data from a particular location. And as you were talking about before, Sharif, you can use those curves to estimate the probability of damage at that location based on the historical storm information about the size of hail at that location.
Yeah.
And
yeah, I think one of the, like, as you look at this chart, you look at these, statistically different populations of materials, they all come with trade-offs. One being weight is the easiest trade-off, like Sharif mentioned, in the history of the area, where there's likely fits, based on regional threats that the solar modules are going to see, that a 2-2 could exist in low threat areas likely, and if you're going after high threat areas, you're going to want to increase that amount at the trade-off of something like weight, as an example, or supply chain type of thing. So I think that is an area, like in general, being new to solar, is that the threat that the area that your module is likely going to see in the field versus how does it need to perform, the cost to performance or weight to performance metric. To think about that is that one size likely doesn't fit all as far as you look at a hail map, and it's clear that there's certain regions that are more highly suspect than other regions when it comes to the threat of hail.
Yeah, thank you. Yeah, these curves can be used with typical, catastrophic peril risk platforms like AIR or RMS, or they can be used by the platform that we have, which we call Sherpa, the Solar Hail Engineering Risk Prediction and Assessment Platform. All right, with that, let me just mention the last couple things I wanted to talk about. So some new services from VDE Americas. We now are able to offer hail modeling across the entire globe, save for just a couple locations in Africa that we're still working on. So yeah, this is exciting. If you have a project outside the United States, we can now provide an estimate of the risk of hail losses at that project using specific module constructions and different trackers or different mounting solutions. We can also provide ongoing independent hail stow verification to make sure that trackers are going into hail stow as expected. And then we can now also provide portfolio risk assessments. So basically batch modeling of, dozens of different projects at different locations, and also correlation of hail damage with projects within a 200-kilometer radius, which is large enough to account for a storm that hits multiple projects within that area. And then finally, I just wanted to mention some free resources for the industry. So we have our technical memo on best practices for hail stow and single-axis tracker-mounted solar projects. So this is basically a guide to implementing hail monitoring and stow for solar power projects using trackers. We have a forensics database that we launched with NREL through the Duramat program. It's a place where people can upload data about hail losses and hail successes and download data freely. This isn't very populated yet, so if you have some data you can put up there, that'd be great. And then finally, I wanted to mention this hail stow risk evaluation form that we co-published with KWH Analytics. This enables developers, owners, and operators to submit information about what they're doing to monitor and stow for hail on tracker systems to companies like KWH Analytics, that's an insurance company, and other insurers, with the idea of confirming that their hail monitoring and stow systems are in place and functional in exchange for better terms on their hail insurance coverage. All right, with that, I want to thank our guest speakers, Sharif and Mike. Thank you very much. Great job, really interesting, and I'll adjourn the session. Thank you very much.
Thank you.
Great, thank you.